So thank you very much. I would like to start by thanking the organizers for the opportunity to present this work here. I am Joao Gonc, and I'm here to present the work I've been developing on energy flow networks for jet quenching studies. I will start with a brief outline of the presentation that I'm going to do. So I'll do a brief introduction where I'll both introduce the physics scenario that we are in, I'll introduce a little bit the problem that we have to solve, and I will then move on to show some results, and I finish off with some conclusions and eventual future work. So in the introduction, I would like to start by talking about the scenario that we are in. So this is heavy ion collisions. The situation that we have is that when two heavy ions are collided, for instance at RIC in the US or at the LHC in CERN, we have a huge matter density, hadronic matter density in a very small region of space. We end up with this kind of deconfined medium where we have what that we call quark-gluon plasma. It's a medium that we want to study, we want to understand a little bit better. There are several probes to study this medium in particular, and one of them that is very interesting for me is actually, let me just change this maybe. So one of the probes that are the most interesting for me is jets in particular. These jets are very interesting probes of the quark-gluon plasma for a couple of reasons. One of them is that they are in very good theoretical and experimental control in the proton-proton case, so we have a very decent baseline to compare against. The jet is also a colorful object, it passes by the quark-gluon plasma, it gets modified by it. But there is a note here that I think it deserves some attention in particular, that even at the highest centralities lead samples, there are a lot of jets that are actually not modified. So basically, they are essentially vacuum-like jets with some kind of lead-lead collision effect that I'll talk a little bit soon. So I will start by introducing the problem. The goal that we want is to discriminate these vacuum-like jets from the quenched jets in a heavy ion collision. The thing is that we cannot do this directly, at least with experimental data. We don't have a sample of heavy ion jets that are vacuum-like and a sample of the heavy ion jets that are very modified. So what we can do instead is use a proxy. We can discriminate between proton-proton jets that are all vacuum-like, and then lead-lead jets, which are a mixture of vacuum-like and quenched jets. And this starts falling in a little bit in the classification without labels paradigm, where we have two distributions that have two populations, and we want to do the classification of the inner distributions, and we do it through the distributions that we have extras, the mixtures themselves. The situation, though, presents some challenges, in particular because these vacuum-like jets and proton-proton don't have these heavy ion effects I was talking about. In particular, there is an effect that will always be there, regardless if the jet interacted with the medium or not, which is the underlying event. So in the heavy ion collisions, the quark-gluon plasma expands very rapidly, and we fill up our detector with essentially a plateau of around 100 GeVs, on which our jets have to be reconstructed. So this underlying event that is huge, we have to subtract it. It's very intense, and the fluctuations are very significant. So you always incur on some kind of fluctuations in the jet themselves once you treat this. And this is the underlying effect, the underlying event modifications that we also have to introduce on these vacuum-like jets in proton-proton, such that we can actually do what we want up top. Medium response, which is the response that the medium has as the jet passes through it, so the modification of the medium because of the jet that then modifies the jet again, is something that helps models identifying these lead-lead jets very directly. In particular, the more the jet interacted with the medium, the more this effect is going to be present, and the easier it is going to be for the model to actually find it. And you see a lot of papers in exactly this problem where they included medium response, but since they didn't include the underlying event that is always present in experiment, the results are not really portable to experiment. So what you need to do is consider this underlying event, contamination, and you have to consider that it's going to degrade back the medium response, the discrimination power we got from medium response, to similar levels to those without medium response. So only by considering all of these effects can we actually approach a physically meaningful result. And here I take the chance to basically do a little bit of publicity. So earlier this month, we finally got the paper on exactly these effects. So here I just present a BDT Hawk curve for an analysis on a very large set of jet observables, not the ones that I will talk about later. But essentially here, the signal only, SO is the blue curve, is what we have if you don't include medium response or the underlying event effects. And you can clearly see, as soon as we get the medium response effects in, we get a huge increase in discrimination. So however, it's not physical. as soon as you basically factor in back the medium, which the underlying event contamination here in the red curve, you end up with something similar to what we got originally with the signal-only event. The paper is there if you want to check it out a little bit. So I would take a little bit of time to talk about the observables that I will actually use. These are observables that came out quite a long time ago. I think the paper is from 2018. And by the time I got this paper, I was doing my master's thesis, and I was thinking about jet observables, like what are the best possible observables, how can I model all of them to eventually feed them to a model. And I looked at this and I thought, great, somebody did the work for me. It is exactly what I wanted, something with the transverse momentum fractions of the particles themselves, so the constituents of the jet, and the angular connections. And they have a bunch of other properties that are very interesting also. One of them is that you can actually associate them with kind of graphs. And the way that you do this is that the sums over the transverse momentum fraction z correspond to dots in the graph itself, and the angular connections are going to be, well, lines, edges. They are very interesting for me also because you can model and basically have very complex kinds of observables that you probably wouldn't think of manually, and you can just represent them like this. More than that, they already have inside in these sets of energy flow polynomials a bunch of other jet observables that we know that were useful. In particular, we have the jet mass, for instance, is associated to a series of these. We also have the two-parameter angularities, and basically this is what I want to say. So these energy flow polynomials offer a very complete basis of the information inside of the jet itself, and they will serve as a baseline. Well, I will talk about neural networks themselves. In particular, these neural networks are associated, that I will talk about, are associated to these energy flow polynomials. They are called energy flow networks from the same people, like 1 year after. I think one of the authors, if not the main author, is basically here in the audience. The essential idea is that we take jets basically as constituents, the particles themselves of the jet. And I really like this idea from the start because this takes the lowest level possible information from the jet already after taking care of the detective effects and experimental things that I try to avoid most of the times. So the idea of these kinds of networks is that for the energy flow network case, that they take the particles in particular as the eta phi representation, so their position in pseudo-rapidity and the azimuthal angle, and then we have a network big phi that essentially takes a particle, takes this two-dimensional vector, and maps it to a vector of dimension L. So you start with a vector, so with a set of vectors of dimension 2, n particle vectors, and you end up with n particle vectors of dimension L of the latent space. You then aggregate this using the transverse momentum fraction of each of the constituents, which kind of gives us a nice property from the theoretical side, which also made me very interested in these models. That is, you then sum up all these per particle latent space vectors, and the way that you aggregate them is actually through the transverse momentum fraction. This ensures that if I add a very soft particle to my jet, that doesn't change the jet, it shouldn't change the observables. The latent space is not going to be changed because the z is going to be very small. It's not going to change the final latent space vector, the aggregated one, the event representation. At the end, these networks pass this latent space directly then to a final F network that gives you what you're looking for, either a classification score or regression or whatever. What I wanted to do is, other than just apply these energy flow networks to this problem, is to try something else. In the original code, it was already possible to add, concatenated with this latent space, some kind of global observables to the F network. So I could, in principle, give to the network every observable I know it's interesting for my problem right there. So the phi network has no gain in actually learning this, and it's going to learn something, in principle, that I don't know if it is there and if it has the capacity for it. So I found this to be kind of a discovery way of new observables, but we'll talk a little bit more about this. I'll jump into results, and I'll start with some baselines on linear models in particular, and I'll start by talking about these energy flow polynomials. Another interesting property is that you can build sets of these energy flow polynomials by the maximum number of connections, and these will be finite. So I can start with just all of the energy flow polynomials that have a single connection, easy to count that one, and I can basically start increasing the number of connections to increase my basis. By the time we get to 5, we have essentially 100 observables. And on the left, I show you basically the curves without the underlying event, but with the medium response. As you can see, everything looks very good, almost too good to be true, because it is. And then once you include the subtracted, you include the underlying event, so you embed both the vacuum and the lead jets in a realistic underlying event, hopefully experimentally motivated, and you subtract them, you see that the discrimination power is heavily reduced. In particular, we go from something like 0.87 to 0.7. Note that we are basically at the same Hawk AUC level, around 0.7, that we were on the thing I showed you from the previous paper. So that's signal-only medium response and underlying event analysis. We can go a little bit further, right? We have a linear model, we have these observables. Let's see, we are going to use them in a neural network. Let's see what happens if you put them in a neural network. Is it better? And indeed, just with a smaller set of basically energy flow polynomials right here, we already start to have some discrimination. It wasn't the case before. So the DNN indeed gets more information that we did from the LDA. And in particular, this amounts to 2%, 1.5 increase in the Hawk UC for the actual physical case. So at this point, we start looking at neural networks. In particular, the energy flow network, that just the vanilla style one, in the sense that I'm not adding any jet observables yet, I can get already a 5% increase from the previous baseline. So we have 0.77, 0.76 of the AUC for the vanilla excuse me, energy flow network. The first set of observables that we actually include are not going to be the energy flow polynomials, but they are going to be the n-subjectinous spaces that are basically a set of observables that are also considered in the energy flow polynomial paper in itself. We gain another increase of around 5%, 4% basically in the Hawk UC. This includes medium response and underlying event. We have 10% since the previous state of the art. Including the energy flow polynomials instead gives us more or less the same kind of discrimination power. We can extend these energy flow polynomials actually. We can basically put different powers kappa to the transverse momentum fractions, or different powers of the thetas, the connections beta. And we can then extend these spaces a little bit. We do not gain that much just using these extended energy flow polynomials. But if we do combine them with n-subjectinesses, we get a better result without the extension. That's what I present here directly. And the state of the art that I reach is around 0.8268. There's a room for improvement here, obviously. I should say that the paper is under construction, as you can see there. Finally, we can apply this kind of classification without labels analysis. We basically do a calculation of the Hawk curve directly, and we get around 0.835, which is a little bit better. And this would kind of be the end of my talk if 2 summers ago I didn't have a very nice summer student, Martin Pint right there, that actually did me the favor of testing out basically what would happen instead of just adding these global jet observables. Let's add particle distances, right? We do anti-KT, we do have these distance calculations that we have to do, Cambridge-Hackam, anti-KT, KT distance. Let's start adding them and see if it helps at all. And I was kind of warned by some people that were working on these kinds of networks that probably adding the distances wouldn't help in the quark-1 discrimination case, which is basically where these energy flow networks, one of the cases where these energy flow networks were applied when they were proposed. And indeed, in our case in particular, we tested for the quark-1 discrimination. It doesn't help at all. Indeed, it's in the backup if you're interested. But we see that if we add the free distance types, we actually get a little bit of an increase of the AUC. So adding distances as well could be something that would be important. Here, n is the number of particles that are being considered for the distances themselves, and it starts basically by the hardest particles, so the ones with the highest transverse momentum. And this again would be the end of my talk. And I was basically almost done with this work when a very nice paper came out, also from the same people associated with these energy flow networks, talking about an extension. So over the last few years, I've seen a couple of extensions of these energy flow networks. You have hierarchical energy flow networks, and you have this moment energy flow networks, etc., etc., etc. This seemed to be one of the most interesting to me because it tackled one of the biggest challenges that we still had on these networks themselves. So the networks were interesting by all of the reasons I said. They take low-level information. They can basically have infrared safety directly embedded in because I had a soft particle, it doesn't change the observable. But the latent space that would be eventually the observables that the network actually learned had to be quite large for one to basically actually have a performant network. So if you have like 256 latent space dimensions, a little bit hard to check one by one and see the observables, etc. Maybe you can average over them, and that's what I did. But you lose a little bit of interpretability of what the network actually learned, of the observable that it obtains when you give it all you know it's interesting. In particular, what it does is that at the point where we were passing this average, this weighted average in transverse momentum fraction of the phi network, that initial network that takes each particle to a vector of dimension L, We then did the segregation and we ended up with a final vector of dimension L. This is basically the averaging there. Is that we can extend this. We don't have to basically give to the F network just the averages. We can give higher moments of the distributions. You can give the standard deviation, the kurtosis, the skewness. And this means that effectively you get a latent space dimension there in the F network in this moment energy flow network case that is larger than the actual latent dimension that you have, larger than the number of observables that you actually have. This was very interesting for me, and the first thing I thought, okay, I need a baseline, so I have to train k equal 1, so this is a vanilla energy flow network, it's just the average that's being passed through, and I'm increasing the latent space dimension. So I start with something like 1, the result is very bad, it's basically random guessing, and there is a point where basically we increase, and we stabilize somewhere. This is a 1024 latent space dimension, it's already very, very large. The second test that you can do is do exactly the opposite, right? You can fix latent space dimension equal 1, I get a single observable, very interpretable in my opinion, and I vary the kappa. And I maybe went a little bit too far here because, oops, I basically went to the moment, the 64th moment of the distribution. Because I hope that, and I hope that doesn't have a name because I don't want to learn all of them from kurtosis to the 64th. But the results are essentially this. We basically get an increase. This is much more unstable. We have a single latent space dimension. You have a bottleneck in your network, essentially. That is a point where we gain nothing from basically keep adding these moments. The second test that I wanted to do is, okay, let's go a degree up. One single latent space dimension is indeed a bottleneck. We can do a little bit better. And we can check up there what happens also if our k is equal to, and we vary the latent space dimension itself. For basically the top plot, we can see that as the latent space dimension increases with the kappa equal to instead of equal 1, we systematically get results that are above what we had before. So we get a result that is comparable to 1024 latent space dimension, already perhaps at 256, 100, etc. The next test that you want to do, or that I wanted to do to test these networks out, can I use them, what is the optimal thing to use, etc., was like, let's do a scan. Let's train as many models as we can. Let's do, basically this is a counterplot of all of these trainings that I did. The AUC is what's on the Z plot. And so we have like this 0.75 result of the vanilla energy flow network that I showed before. And we trained all of these models. This is for kappa, this is for the latent space dimension. This is like the good model or the best model for with the highest latent space dimension in the vanilla case. And you can see that for kappa equal 4, you can actually get a very comparable result to this with just 8 dimensions. I can go through 8 dimensions, I cannot go through 1024. The reason why we don't go higher from this is that there is a point where the effective latent space dimension, what you actually feed to the F network, becomes ridiculously large. In fact, if I go closer to this corner here, it becomes closer to the number of particles in the known universe. A little bit too big. We tried to also reproduce a little bit the work that was done in this paper originally. So they plotted basically 1 minus the UC across a bunch of trainings for kappa equal 1 and kappa equal 2, 3, and 4. And the interesting thing is that instead of plotting this against the latent space dimension, if you plot it against the effective latent space dimension, the curves almost that fall perfectly on top of each other. And this is kind of the behavior that you expect. As you increase the number of information that you give to the network, you get better results. And this is all comparable. You can start looking then at some latent spaces. So this is the average over the latent space of the energy flow network for all of these 1024 observables there. We get something around 0.76 on the test set. And we can see that we have kind of how do I say this? I'm missing a rotation symmetry situation here. Basically the thing is more or less the same around. There are some fluctuations here in the middle. But it's hard to interpret what's going on, especially because this is 1024 dimensions all jumbled up on top of each other. And, well, let's look at the case where we have less dimensions, perhaps 16 dimensions. And indeed, we have basically a very comparable result, compatible within the cross-validation uncertainty. That's what I used for the uncertainty here. And we see that the latent space is still very not interpretable. What I would like is then to basically try to fit this. This is what they did in the paper. They chose a preferential direction because of this rotation symmetry, and they fit basically this distributions. I have here the 2 cases, so one of them the fit did not converge, and I'm essentially fitting what they fitted, but what they did is fit one dimension with one thing, fit another dimension with another thing. I just summed basically the 2 fits since I'm doing basically the average latent space itself. And of course, we want to add observables to this, right? We want to give it all of the information that we know that is useful for this discrimination. And now that we eventually get a manageable latent space, maybe we can then look at that and see what it learned. And indeed, for L equal 2, only 2 dimensions, and for K equals 64, so the 64th moment of the distribution, we again get this rotational symmetry, but there is some kind of weird modulation that maybe is hard to actually interpret. We can go further, we can use a single latent space dimension. Things start to get weird. For some reason, the network starts to basically learn this kind of shape at the 16th moment. I am not sure if it's because of the kappa that I'm using, but it is what it is. And we can actually do very good results if we are already giving information that we know are relevant with simple moment free of the distribution and a single latent space dimension. This because I'm adding a lot of observables that are already doing a lot of the heavy lifting, which means this would be something that the network did not learn. I honestly thought that these things were kind of noise until in CERN later this year, basically, there was a guy that convinced me that this modulation might be actually a feature that the network is learning. And this is something that I'm still trying to understand a little bit better, and I want to talk with more theorists to understand actually, could this be something that the network is actually learning, or is it noise, or etc. With this, I do my conclusions in my future work. So for energy flow networks and polynomials, they seem to capture very relevant information for this particular problem. Adding global jet observables to these complex physics-motivated networks seems to be indeed beneficial, significantly improving the originally attained discrimination power. And moment energy flow networks open up a new window of exploration for these kinds of models to multiple problems in HAP in general and in jet quenching in particular. Future work will be focused on adding other observables to these moment energy flow networks and attempting to obtain an interpretable latent space, perhaps relating it to actual calculable observables. We'd like to theoretically be able to calculate the observables that we actually get from the network. So what observable will the network learn if I give it everything? I think this is a very relevant question. And can we relate this directly to the jet quenching phenomenon? And with that, I thank you for your attention, and I'm open for questions.
Thank you very much. Any question? So I have a quick question. So at some point you defined some notion of effective latent space. So can you say something? So can you explain a little bit more what's going on here?
Yes. So imagine that you're taking a latent space dimension of 1, right? So basically in this scenario, the scaling is relatively easy to understand. You'll have a single observable that's getting into this F network here. Now if you take the moment energy flow networks and you take, for instance, kappa equal 3, you're taking 3 moments of this distribution. So you're taking the average value here, the standard deviation, and eventually what comes next, the kurtosis, the skewness, etc. So this is what I mean by effective latent space dimension. In this case, 1 would be your latent space dimension, and 3 would be your effective latent space dimension, so the information that you're actually feeding to the final network. So that's it. I'm not sure if it's...
Can you go to the plot where you show that the behaviors match when you...
Almost match. The authors of the Moments Energy Flow Network paper are more confident that this matches very well than me, but I think that, at least in the tail, it does perfect. Like this is it's getting better. When before, for instance, you had this K equal 3 model here, it's the highest L model that we have. Here it's there. So it's hard to here kind of understand how things are all on top of each other. With that next plot, you can actually see it. That is this effective latent space increase that is driving the increase of the discrimination power.
Okay.
Thank you.
Any more questions? Okay, if not, let's thank all the speakers of this session.